So today we've been all day at the City Institute, which is the search for extraterrestrial intelligence. You have its mission here, and we've had an introduction by the director who explained the mission, and we've had some discussions about the Allen radio telescope array and its possible use in the Euroluna X Prize. Then this afternoon we've had a visit to the AMES Research Center of NASA, just north of here, and I have taken a few video shots of the wind tunnel and the heat shield test facility, which you will see now. So this afternoon we're visiting NASA AMES facility, and inside the 11-foot wind tunnel facility is where we are right now. I would say that for a facility 50 years old, it's looking quite good. The motors and the place where we're going to go in and see where they place the models later on. It's looking impressive from out here. And just to show you one of the models, which is on display of the vehicle capsule here, with strain gauges on for measuring inside the wind tunnel. And the facility as such, there's a little overview here. The central motors and the two wind tunnels in one direction and in another direction, with different options for speed, subsonic and sonic, and different cross sections depending on what the test needs to test. So here's a view from where the air is actually flowing in order to deliver for this 11 by 11 foot, which translates into 3 by 3 meters, or close to it. And this is good. Compressors. So this is the outside of part of the wind tunnel.
Absolutely, yes. We were covering that earlier. We're currently working on international agreements with other customers, and typically there's a document put in place where we have to work with the details, and that is definitely acceptable for the type of business that we're doing.
That's right. So what happens is, unfortunately, this is pointing the other direction. So this hot gas flows out of the nozzle into what we call free stream. And from left to right, it impacts on the surface of the test article. These are representative of geometries, different materials, different programs. This is a little small half-tune diboride, about an inch in diameter. What happens is with smaller models, sharper models, you can get higher surface temperature. There's a very large, we call it a large blunt body, so this is 24 inches in diameter, so bigger than a basketball. Different flow conditions. This is actually a section of a wing leading edge from X-34, which is a wing re-entry vehicle. So just chop a section of the wing and put it on the end of this arm and immerse it in this hot plasma flow. In fact, the facility that we're in this building here, covers the entire block. There's a lot of equipment, including DC power supply. So the power that goes in to the arc discharge in these facilities is 20 megawatts to 60 megawatts DC power. So enough power for a large section of a city, converted to DC electric power and then fed into the arc heater. There are actually multiple arc heaters in this complex that we have. So we actually have what we call multiple facilities, although it's kind of all lumped into one large category, one of arc jet facility sharing the systems. There's a vacuum system, there's the DC power, there's a large cooling tower. These arms are all standing up that are L-shaped. One at a time they pop up with a sample held at the end. One at a time they will swing into the flow and hold the sample in the flow. Now those are water cooled so that they survive. They get severely heated as well. You see the rapid high pressure water flow, high velocity water. And the sample is heated, the surface temperatures can be, well, we've achieved hafnium diboride surface temperatures of over 3,000 C, and a typical surface temperature would be 1,500 C to 2,500 degrees, 15 feet long. And there's electrodes at either end, anode and cathode, right? And our cathode or electrode has electricity flows plus to minus. And the anode and the cathode, these green cables, and I'm stepping out with my foot, those are power cables, electrical power cables that come up, connect here from the power supply that's that substation that you saw in the photograph. It's actually a quarter of a mile away. And then there's a similar set of cables at the other end. So the electrical power comes up and is connected to here. It then enters this stream through these water-cooled electrodes. Now the reason for all the tubing is it's water cooling. The device itself is highly water cooled because it's generating hot plasma, so it's in a tube through which the arc discharges. So the arc will discharge down the center of this tube, where my finger is. That's the electrical arc discharge. That's a steady, continuous arc. It's not like a lightning bolt which flashes on and off. This is a lightning bolt that flashes on and stays on. It's much more like a welder. Like an arc. An analog computer. I don't know if you noticed the color on the floor. There's an analog computer sitting here that was the data acquisition, data recording system when I studied. It was data from the 60s. So, okay, we've updated that. Okay, at least we've gotten that far. Because we went to a digital data recording system, and we've upgraded a lot of the systems, but not just the facade of the panel. It still looks like it did, and it kind of has that 60s look. It was built in 1961, went into operation 62 for Apollo. So some of this equipment, although it's maintained and it's calibrated, it's some of the big gauges. Now I'm told also that the big gauges are the large, with the big scales and the large numbers, was because the old data system, when you ran a test, you'd get your data back. You wouldn't get it back until hours later and sometimes the next day because of the old analog computer systems. It took a long time to process the data. So they had their data acquisition system here, which was a Polaroid camera, which you could reach up and click, and you would now have a picture at least of all the voltage, current, the pressures, and the flow rates, so that you'd have a quick way of returning what was your test condition, because you want to turn around and run another test the same day, and you can't wait. In the old days in 1962, you couldn't wait a whole day to get your data back. So that's the reason why these numbers are so large.